In lesson 2.3, polynomial functions, you will learn to use the leading coefficient to determine the end behaviors of those functions, of polynomial functions, determine the coefficient and power of a function from a graph, and you're also going to use a graphing utility, a graphing calculator, to identify key characteristics of polynomial functions. So let's begin with what a polynomial function is. Now, a polynomial function is going to be a function that's written in standard form like this, where it's just simply, again, a list of monomials being added or subtracted together, where the coefficients an, a sub n minus 1, and so on are real numbers. So these values, again, are just any real number, negative, positive, fraction, rational, irrational, again, any real number. Now, a polynomial function is a smooth curve with no breaks or gaps, and they're going to be continuous for all real numbers. So there's no holes, no jumps, no type of discontinuity at all. So they're continuous, where every time we change direction, we change direction by using a smooth curve at those turning points. So something like this, or downwards like that, compared to this. These two right here in red are not how polynomials change direction, okay? They change direction in smooth curves, where we have a maximum and a minimum, relative max and minimum, at those turning points. Now, we can determine the end behavior of our functions by using the coefficient and degree, by using the coefficient and degree, or degree and coefficient, of the leading term. So the coefficient and degree of the leading term determines how the graphs are going to behave, the end behaviors of our function. So we use, again, the same procedure and technique from our power functions for a polynomial. We have this polynomial. In order to determine if this polynomial is going to behave like this power function here, we simply have to look at the leading term. So all we have to do in order to focus here and determine if our two ends are going to be pointing upwards is to look at the leading term and know what causes the two ends to point upwards. So for a power function, in order to look like a quadratic right here, our value of a, which is right now a sub n, that has to be some positive number, some positive real number. Again, fraction, decimal, rational, irrational, but it just has to be positive. And our exponent of n has to be an even value. So as long as these two values, this value is positive and this number here is even at the very beginning, then it's going to behave like this power function there, where the end behaviors are going to be both pointing upwards as we make x really, really small, a negative number, and x a positive number, a very large positive number. Now, if all I do is reflect that, flip that downwards like this right here, our polynomial is the ends of our polynomial, these ends are going to be pointing downwards and behave like this power function, just as long as the first term, our leading coefficient and degree, again, has the same characteristics, where a is going to be some negative number and our exponent is still going to be some even number. Because all we're doing is just simply reflecting it, so it behaves again just like that power function there. Now, of course, because of all of these extra terms right here, the graph is going to curve several times up and down, and the middle part is obviously not going to intersect at 0, 0, and it's going to intersect at different places on x, but the overall end behavior is going to still behave exactly. So this function here will end up behaving like this power function, where our x coefficient is negative and our exponent on x is an even number. So for the next example, like this one right here, in order for our polynomial to behave like this power function here at the ends, again, focusing only on the ends, for the ends to be pointing to negative infinity and to positive infinity at the left and right end respectively, this polynomial function needs to behave like the power function a sub n times x to the n power, where our coefficient is going to be, again, some positive number, and our exponent is going to be an odd number. And again, just to emphasize this, because of all these extra terms, the graph will curve several times in and out, up and down several times, but the end behavior of the function will still be the same. The left end will be pointing down and the right end will have to be pointing up. And then if I flip this and have the left end point up and the right end point down, again, as indicated through this right there, our polynomial has to behave like the power function, where our coefficient is going to be now negative and our exponent is still going to be odd. So we can determine the end behaviors of any polynomial function by simply focusing on the first term. And the first term behaves, the ends again behave the exact same as the power function with those same characteristics. All of this, all what this extra stuff does that we add to the power function, it just simply transforms it, so it makes it curve up and down several times. But again, the overall behavior at the end is going to still be the same as the power function with the same characteristic. So for example, this function right here, to determine the end behavior of this function, we just simply have to compare this polynomial to the power function f of x is equal to negative 1 times x to the power of 4. Simply focusing on that one there. Since this power function here will look like this, oh, sorry, not wrong one, not like that, will look like this. Since this power function will look something like this, then that means that this polynomial is going to behave very similar to that, where the two ends are going to be pointing downwards. Of course, because of all this extra stuff, it'll curve up and down several times, but the end behaviors are going to behave the exact same way. So as x approaches negative infinity, we'll see that the y values, the function values, are unbounded, pointing downwards, pointing towards negative infinity. And as x approaches positive infinity, the right end is also going to be unbounded, pointing downward. So the y values are going to approach negative infinity as well. So this is the end behavior of our function. Let's look at another example, this example here. So here, this polynomial, the end of this polynomial is going to behave the exact same way as this power function here. So this power function, because we have a negative coefficient and an odd number, that behaves like this, where the left end is pointing up and the right end will be pointing downwards. So this polynomial behaves the exact same way. So as x approaches negative infinity, the left end is pointing upwards, unbounded. And as x approaches positive infinity, the right end of the function is unbounded, pointing downwards. So it's approaching negative infinity. So it behaves the same way as the power function. Of course, and I know I sound like a broken record, but this extra part there just simply makes the graph in between the two ends simply curve up and down several times. That's it. So it doesn't behave exactly, it doesn't look exactly like this, because obviously this is going to transform the power function, but the ends will be pointing in the same direction. So continuing with that, to determine the end behaviors of this function, simply look at the first term, the leading term. So we have 1x to the fifth. So since 1x to the fifth, that power function behaves like this, that means that as x approaches negative infinity, this polynomial will be unbounded, pointing down, going down. And as x approaches positive infinity, our y values to our polynomial, to this function here, again, are going to be pointing upwards. So unbounded towards positive infinity. And this last one here, this polynomial will behave like this power function, like 2x to the 6. And 2x to the 6 is like a polynomial. Again, it's like a u pointing where the two ends are pointing upwards because this is now a positive number and this is an even exponent. So this polynomial, again, with all of these extra terms, all of this will make the graph, again, curve up and down several times, but the two ends are still going to end up be pointing upwards. So at the ends, for this function, for this polynomial, we'll see that the left end is pointing upwards, unbounded, and the right end is also unbounded, pointing upwards. So this is the end behavior to our polynomial function. Now, the number of times that it curves up and down is still depending on this value right there. So all these extra stuff, again, that we add and subtract right there makes the polynomial curve up and down. Now, how many times can it curve up and down? There has to be a limit to that. And that is corresponding, again, to the number of turning points. Now, the point at which the polynomial switches direction is referred to as a turning point. Now, turning points are defined where the function is increasing and decreasing, it defines where the function is increasing or decreasing. So obviously, if a graph has one turning point, this turning point right there, it tells me where my function is going up and where the function is going down. From left to right, I go up. When I reach this maximum point, this turning point, my graph then goes down from that turning point on. Now, the number of times that the turning point or the graph turns is always going to be 1 unit less than the degree. So the degree of the polynomial is always at least 1 unit higher than the number of turning points. So the degree is always greater than or equal to the number of turning points plus 1. So if I have this polynomial here, again, this polynomial of degree 6, then I know my function can only turn 5 times. 1, 2, 3, 4, 5. A maximum of 5 times. I cannot have this polynomial turn 1, 2, 3, 4, 5. This many of times. 1, 2, 3, 4, 5, 6, 7. It cannot turn 7 times. It could only turn 5 or less. It's always going to be 1 unit lower than that. So it could turn 5 times, it could turn 3 times, or maybe just 1 time like this, but it cannot turn more than 5 times. And it can't turn 3 or I didn't say 2 or 4, because if I turn 2 times, 1, 2, then the graph is pointing in the right direction. So it has to be an odd number of times that it turns. Since 6 minus 1 is 5, it would have to turn 5, 3, or 1 time. Because if I use an even number of turns, then it doesn't match. The directions is not pointing in the same direction. So if I'm given a graph, I can determine the leading term. I can figure out the leading term and the number of times it turns by looking at this value here. So for example, here, I know it's a polynomial. And I have all these other terms again that are being added. And I just want to be able to figure out what is the coefficient going to be And what is the degree going to be? Well, since the two ends are pointing in opposite direction, where the left end is pointing downwards and the right end is pointing upwards, that's similar to, again, the power function that behaves the same way. So like this power function. And this power function, the coefficient is going to be some positive number, and the exponent of n, this value of n here, this exponent, has to be some odd number. Now, because of the number of turning points, 1, 2, 3, 4, 4 turning points, I know this odd number of n has to be a number that's going to be greater than or equal to 5. So I know it has to be 5 or higher, 5, 7, again, 9, whatever. But I know it has to be an exponent, an odd exponent greater than 5. So let's look at another example of how to determine the leading coefficient. So like on this example, again, we're not going to know the exact value for the coefficients or the exponents, but here we have some polynomial again. And all we want to do is be able to determine what is the coefficient and what is the exponent for this thing. What could it possibly be? Well, in this situation, since the two ends are pointing downwards, this is going to behave like the power function. Any power function, again, like this, where the two ends are pointing downwards. Well, in order for the two ends to be pointing downwards and behave like this power function, we need the value of a to be a negative number, and we need this exponent to be an even power. Now, what's the smallest even power, or what's the smallest even power that we can have? Well, because of the number of turning points, 1, 2, 3, 4, 5, because of the 5 turning points, that means that this exponent of n has to be some even number that's going to be greater than or equal to 6. Always one unit higher than the number of turning points. Let's do one more. So for this one, again, this is a polynomial, and I know it's a polynomial because, again, when it turns, it's smooth, the curves are smooth, and there's no holes, no gaps, it's continuous. It's one continuous function. So I know it's a polynomial, and it's going to have, again, this general form. And all I want to do is be able to identify what is the exponent and the coefficient for this polynomial going to be. Well, our coefficient, because this graph behaves like this power function, I know that that leading coefficient has to be some negative number. And because the two ends are pointing in opposite direction, I know that has to be an odd number. And in order for the top end, for the left end to point up and the bottom end or the right end to point down, I need this number right there to be negative. Now, because of all the stuff that I'm adding to it, of course, it curves up and down several times. And because it changes direction 1, 2, 3, 4 times, it has 4 turning points. That means that this exponent up there, n, has to be a number, an odd number that's going to be greater than or equal to 5, 1 unit higher than 4. And that's what we can determine about the leading coefficient, that our leading term. We can identify that about this situation here, that this number has to be some negative number, that the exponent is going to be an odd number greater than or equal to 5. So 5, 7, 9, any of those will work. Now, in order to figure it out, of course, we would have to know more information, like where we're crossing the x-axis or something else, in order to figure out the actual value, but we're not going to go that far. Now, in determining characteristics of these functions, we would have to graph this function in order to determine how, again, the graph is behaving. So let's get our graphing calculator out. Where's our Desmos? Here it is. Okay. So we're going to type in x to the third power plus 9x squared plus 2x plus 21. So x to the third power plus 9x to the second power plus 2x plus 21. Sorry, I keep forgetting. Plus 2x plus 21. Okay, let me zoom out. And I like losing decimals because I like the fact that I can just click on the graph and it tells me all the key points that I'm interested. Like right here, I'm looking for the turning points. So my max and min values. So by clicking on it, it automatically identifies where the maximum value is and where the relative minimum value is. So I have that point right there. So I have relative max at negative 5.89, we'll say, set 117.3. So let's write that. I have a relative max at negative 5.89, 117.11. And I have a relative minimum at, and I'm going to zoom in right there, down there. You could see that there's 2 points, and I have a relative minimum right there at negative 0.11 and 20.89. Negative 0.11 and negative 20, positive 20.89. Now the graph is increasing again. So it looks like this, and it's going up, going down, and then going back up again. And I did not draw this correctly because it doesn't go below the x-axis, as you see right there. So let me fix that. So it goes up, it goes down, and it goes back. And it reaches a maximum right there at this point at negative 5.89. And the minimum value is right here at negative 0.11. Of course, with the y values. But the y values are really not important for this next part here. Because from left to right, the graph starts by going up. We're increasing from negative infinity to we reach this point right there where the x value is negative 5.89. And then it starts to decrease until we get to that minimum value there. So it decreases from this negative 5.89 to this point here where the x value is negative 0.11. It obviously changes direction because that's the minimum. It changes direction and the graph then goes up again. And it's going up again from that changing point where the x value is negative 0.11 all the way and for the rest of its continuation, which is all the way to infinity. And it's not infinity because it's pointing up, because it's infinity because we're moving again to the right. So from negative infinity to this point right here, to this turning point, the graph is moving up. between this turning point and this turning point right there, in this red section, the graph is going down, which again is between this x value and this x value. And then finally, between that x value all the way to positive infinity, the graph is moving in upwards direction. So these are the behaviors, and again, where the function is increasing and decreasing in terms of interval notation. So these values, again, are x coordinates. They're not in x and y. So don't get it twisted. This is not x and y. This is x1 to x2. This is x1 to x2. And we're decreasing from this x1 to this x2, which is from here to there, where the x is negative 5.89 and this x is negative 0.11. And I like using decimals because, again, it just makes it simple to find where those turning points are located at. Just simply clicking on the points. Okay. So there you go. I have one more. Yes, I have one more to do. Let's see. Let's do this last one example right here. So let me graph this one. Okay. So let me get the decimals out. Let's delete this and let's see. Let's type in this one. This is x to the fourth power plus x. No, I'm sorry. Minus x to the third power minus 4x squared plus 1. So I want to find first here we go. I want to find first where the relative max and mins are located at. So let me just mess around with, there we go. Let me just mess around with this. Okay, and here is a minimum value. So here's a relative minimum value at negative 1.09, negative 1.05 for y. And then we have another relative minimum value down here at positive 1.84, negative 7.31 for the y. And then we have a maximum value here at 0, 1. Okay. So let's look at those key characteristics. So our relative max is at 0, 1. That is an x and y value. And our relative minimum is at 2 places. We have a relative minimum at negative 1.09, negative 1.05, and 1.84, negative 7.31. All right. And the graph, the behaviors of the graph again, the left end is pointing upward, so it goes down, it goes up, it goes down, and then back up like this. And as you can clearly see again, the left ends are pointing upwards, and that again correlates to the power function of x to the fourth. So where the two ends are pointing upwards. And let's see where the function is increasing and decreasing. Well, from negative infinity, so from negative infinity until we reach this turning point, so from here to there, the graph is moving, let me do it in red. From here to there, the graph is moving down from left to right. And then because the turning point just simply switches direction, that means then in the next section, until we get to this turning point, the graph is going to move up. It is moving upwards. It changes direction to go down until it reaches this minimum point there, and then changes direction and moves up all the way to the end towards positive infinity. So we are increasing in these two sections here. We're increasing in this section here and increasing in this section there in blue. which the x values there, this x value down here, that's at negative 1.09, and the x value up here is 1. So we're increasing from negative 1.09 to positive 1, and then we're increasing from this minimum point there all the way towards to the far right, where the x value down here is at 1.84. So from 1.84 all the way to positive infinity. And then there's two intervals in which we're also decreasing. We're also decreasing from negative infinity to this minimum point there. So from negative infinity to the minimum point, which this minimum point has an x value of negative 1.09. And, which I forgot to use that notation on the other one, I'll put it right now. And we're also decreasing from this turning point till we reach this turning point down there. We're going down in that section there where the x value is 1 and this x value is 1.84. So we're decreasing from x value of 1 to 1.84. So from there to there. And here I just need to put this. I need to put a u because there's two intervals in which the function is decreasing. So we're increasing from this x value to this x value, and we're increasing from 1.84 all the way to infinity, and then we're decreasing in these two sections from negative infinity to this point there where the x value is negative 1.09, and from this point to that point where the x values are 1 and 1.84. So that concludes again my examples on this. Hopefully again there were you understood them and they were easy to follow. If you do have any questions though, again, do not hesitate to send me a message on email or ask or on Remind. And again, I appreciate you watching and I hope you have a great day. Goodbye.